Okay, hello everyone. My name is Peter Smith, and I'm here to talk about the somewhat riveting topic, at least from what the title of functional safety and development tools. Now, I'll try and make this. I would say what's the opposite of a dry talk, but I think a wet talk is probably not a good idea for that either, certainly not with all the electrical equipment in the room. So I'll get going as soon as I can. So I've got probably about 24, 25 slides. This is quite a big topic, and you can go with lots of jargon here and there. So if I do say something and I haven't yet defined it, just let me know, and I'll see if I can give you a quick explanation of what it is. So, what am I trying to get at here? So, my aim at the end of this is for you to understand some of the basic concepts of functional safety. Now, I know that there'll be a few people in the room here who will all have a reasonable idea and know what these are. But I'm making the assumption that there will be people in here who don't quite know what functional safety is and how it relates to software. How it relates to software is further sort of specialised in how does it actually relate to development tools, and that's where the area that I've actually got most of my experience in. So that's the area I'll probably be focusing on, but I will make a few comments here and there on some of the stuff on the other side. So one of the other things that I can sort of help out with is some of the steps that what would somebody developing one of these safety-related systems have to know about development tools and software. And I've introduced two words here that I probably will need to define later on, which is qualification and certification. That's an important thing about the sort of requirements of the functional safety standards. One of the main reasons for me being up here and talking about this is I've been involved in the qualification and certification of a compiler back at ARM, and I'm sort of here to share some of my experience with that. And then, if you allow me to speculate a little bit about, what does all of this qualification and certification mean for open source tools, and how does this relate to Monaro as opposed to, say, a commercial sort of software product? Okay, so what's my background in all of this? Well, mostly I'm an engineer, so at the moment I'm assigned to the toolchain working group, and I work on toolchains, mostly linkers. Being around in a toolchain group for an awful long time means you pick up an awful lot of knowledge about how the tools work together, where all the faults are, why decisions were made at certain times, and it kind of makes you one of the perfect sorts of people to write what's called a safety manual and pull together all of the information together for a sort of certification qualification. So I was heavily involved in the production of the ARM compiler sort of qualification kits. That's kind of where my sort of path as an engineer and my path as a document writer crossed for a sort of certain period of time. So, first stage of the talk, I'm just going to go into a little bit about what functional safety is and how it's related to software. Okay, so at its most basic level, functional safety comes sort of from the sort of hardware side of things. So it's very much, you have some sensor, there are some sort of inputs that come into this sensor, there's some sort of logic that says, as a result of this particular input, I will control some hardware that will do something. So I've just given a couple of examples there of a sort of sensor at the back of a car, that those are the sorts of things that when you reverse, they'll beep when you're about to crash into a wall. And on the right-hand side, there's an industrial robot, which is obviously a lot more complicated. And the interesting thing about the device on the left is it's only providing you with information. The human is still the one that makes decisions. But the device on the right, if you can imagine a device at that size, if it swung around and you were in the way of it, then there could be serious consequences for the human involved. So generally, functional safety it's governing a device that controls hardware. It's got some inputs and it's got some outputs. And the reason it's called functional safety is that that device has some kind of specification. It'll be, what do I expect to happen when I give it this input? I should expect this output to happen. And it's really about what sort of things can I guarantee, what is my functional specification of what I do as a result of my input. And the safety part is basically, how do I make sure that this thing isn't going to be a danger to humans? So this is sort of, as part of my, this is a huge topic, there's loads of details. When you actually get down to it, there's actually a very small amount of underlying principles that you can apply. And quite a lot of it kind of derives from these sort of underlying principles, and a lot of it is just when you're trying to understand the functional safety standards, think back to the principles and say, well, okay, what makes sense in light of these principles, and I'll sort of try and go through these. So the first thing is the important word is context. So one of the things that you'll notice is the functional safety can vary from a medical device, a car, a nuclear power plant. These are hugely different contexts, and they all present very different risks. So it generally means that you can't ever look at anything in isolation and say, this is safe. It has to be understood in the context of the whole system. The sort of rather contrived example is you might have something that's completely safe on a car, but if you put that into the middle of a nuclear reactor, it would just melt. So the chances are you have to map what you're doing into a context. So that's one of the things that you'll find is that if you're a vendor of a component that's being bought or integrated by somebody else, it's the person doing that final integration that bears all of the costs of ensuring functional safety, because it's only them who know the context of everything that's happening. Similar to that, or related to that, is that functional safety doesn't compose. If you have 10 functional safety or functionally safe components and you put them all together, that doesn't make a functionally safe system. The different parts of the system can have different levels of safety, so typically what would happen in a design, and you'll see this quite often with the automotive side, and you might have heard that with some of the talk in the keynote yesterday of the high integrity parts and the low integrity parts. So in general, what a designer will do is we try and say, this part is high risk, and that's the area where I've got to concentrate most of my resources on. This part of it, I've isolated it, and it's not actually impacting any safety-related function, so I don't necessarily need to go through all of the rigmarole of the functional safety standards. Okay, so you'll often see these things called SIL or ASIL. I'm not going to go into these in too much detail, but they're basically a sort of a measure of how, of the level of risk. So ASIL runs from ASIL A to ASIL D. Something like ASIL A and B are things like, I think entertainment comes under sort of A and B. Something like a self-driving car will come under D. So obviously the self-driving car has got much more opportunity to harm someone than their infotainment system, you would hope. Yes,
depends on the music.
It depends on the music, depends on the driver, all of that sort of things. The assumption of a sane human driving a vehicle, yes, very difficult. Yes, the human driving test probably not so good overall. But anyway, so the first thing about hardware is allowed to have random faults. Software isn't. So if you have a hardware device, it's subject to the elements, subject to elements outside of your control, and a lot of the way that the safety standards mitigate risk is to actually associate some kind of probability with devices failing, and they have to, when they're showing their safety, that the devices meet a certain level of safety. With software, you can't get away from that. They basically assume that your software, cosmic rays outstanding, will run the same code, do the same thing every time, so that if there's a failure, it's a bug in the software. And that you reduce that software through a rigorous, you reduce the chance of that failure with a rigorous development process. And the software in itself doesn't present a risk to humans. Those of you using certain Microsoft Word products at certain times, or when it crashes or whatever, they're nothing. We don't print manuals for you to cut your finger on it anymore, that sort of thing. So software in itself doesn't produce a risk to humans, but it may control hardware that does. Okay, so with all of this risk and functional safety, there comes functional safety standards. So the two ones that I'll probably be covering most here are ISO 26262, which is the sort of automotive standard, and IEC 61508, which is the sort of, I guess you call it the grandfather standard that mostly comes from industrial process controls. Now what they do is they are not a development process in themselves, these documents. They don't say, you must develop your software this way. What they sort of assume that you have a development process, but what they kind of are is, requirements on your development process. They basically say your development process must cover these particular aspects. Like it might say that you have to have a certain level of test coverage in your development process, or you must show that you've recorded all of your known bugs, that type of thing. So they're really a kind of layer on top of your existing development processes. They're often structured as a V model, so for those of you familiar with the sort of traditional software V model, the idea is you've got your own development process, and you kind of do a mapping of your development process to the V model so that the people doing this sort of assessment can say, oh yes, I can see what's going on. And you can be quite creative with this.
What is a V model?
So the V model is kind of like, if you remember a waterfall model, where you start at the top with requirements, then you go to design, then you go to implementation, then you go to, it's basically that long line. The V model cuts it halfway, where you go to implementation, then it goes back up again, and then you kind of, the idea is it's like a waterfall, but you have feedback levels at all levels, so you get, it's kind of a modified V model. Okay.
No? Not seen it before?
Okay, so one of the V model was very popular in the 90s, 80s, that sort of thing. But it kind of, I think it exists more as a tool of communication rather than saying that you must have a V model of development. So what you have required for sort of compliance to these standards is you have to show documentation. You have to basically make a case, what's sort of known as a safety case. You kind of say, I reckon I'm compliant, and here is my evidence to show that I'm compliant. And quite often that means you've got to show traceability throughout your development process. So you'll hear me mention traceability quite a bit. And that's where a lot of the pain comes in the development process, because it's kind of, a lot of the development process that you'll actually use to develop your software is the same. The difference is you've got to show a lot more traceability from the requirements at the top all the way to the object code at the bottom, and that generally requires extra bureaucracy, that type of thing. Final bit about functional safety standards, if you actually ever try and read them, they are written to be what's called intentionally vague. So what that is, you will never find that they actually ever tell you precisely what to do, mainly so that they don't restrict their scope. So the whole idea is that, say something like ISO 26262 covers the whole of automotive. If they were very prescriptive about what they said you had to do, that would limit the scope to which they could apply the standard. The intention is always, you're the person who's making the product, you know best, you make the case, and you make the justification, and you provide the evidence to back up, and it's up to you to convince somebody who's an expert with the standard to take your case. So, but it can be quite frustrating when you read it and you go, what does that even mean? Okay. So, going on, I'll sort of start speeding up a little bit because I've got quite a bit to go through. But one of the interesting things you'll see is there are lots of functional safety standards, and why are there lots of functional safety standards? And one of the reasons for this is that industries are very different. So the sort of master or sort of grandfather of the industry is IEC 61508, and a lot of the sort of functional safety standards are derived from that or very similar from that. So why would an industry want to do its own thing? Well, if you consider, say, automotive versus, say, industrial plants, industrial plants are pretty much bespoke. If there's a disaster at, say, a chemical plant or nuclear plant, the amount of damage that could be caused is huge. With a car, there's a huge amount of opportunity for commoditization of development, whereas there's only so many factories you could spread any particular costs out of. Cars are far likely to be be able to share technology. Also, what's the worst that you can do to a car other than crash into a chemical factory and cause one of these other things? It's sort of they tune the standards to their local areas. Okay, so I've gone very quickly through what the functional safety standards are. I'm now going to go towards how do you actually map this to a development tool. Okay. So this is the sort of typical model that the functional safety standards have of a development tool. So the first one is a tool that actually modifies the model of the system. So if you think of the source code, the developer starts with their requirements, goes down to their design. They finally implemented that design in a formal notation called source code, whatever source code that happens to be. And then you have a tool like a compiler that's going to transform that source code into object code. Now, in theory, the source code and the object code are both the same thing. They're just models of the system at a different level. But the compiler, in doing that translation, could have introduced a bug. And in that case, you've got perfectly a good model of the system on the source code side, and you've got a potentially flawed system on the other side. So development tools that actually modify the model of the system and the output actually goes into the final system are the ones where the major amount of lines are put in the functional safety standard, because those are the ones that can actually inject bugs into the system. Second type is your tool fails to detect a defect in the input. So there can be plenty of times when you've used a compiler, for example, where it gives you a warning you're about to do something particularly stupid, or an error message saying this is not conformant to the syntax, or you're doing something obviously wrong. So that can catch errors before they make it into the system. So a potential defect here of a safety-related tool or development tool will be it fails to spot one of these obvious errors and it leaks an error into the final system. The final thing, and this is where tools like debuggers come in, is a debugger doesn't change the output. So if there's a bug in the executable beforehand or afterwards, the debugger doesn't change that. But a debugger could, for example, by lying to you, it could say, for example, you were viewing the memory, and you're saying, no, there's no problem here. But in fact, if it got the different memory address and you were looking somewhere different, it could give you a false sense of confidence about what was going wrong. So typically, this is the way that a sort of functional safety standard will view development tools, and this is sort of how you as a tool chain developer have to sort of present your tools in terms of this type of model. Okay. So what actually has to happen for the development tools and sort of in functional safety development? So all development tools must be evaluated. So it's quite a vague statement about what that actually means. And that can mean every tool that you have in your system. So one of the things a safety-related developer has to do is look at every tool, including their source code editors, test generators, Perl scripts that generate test data, that sort of thing. All of those are classed as development tools. Compilers, linkers, assemblers are obviously part of that. And then they need to look at how those tools fit together, how their developers use those particular tools. They have to say, well, okay, looking at that fault model on the previous page, what could go wrong, and how could a consequence of a fault in that area go all the way down the system and into the tool? And then they have to say, well, okay, how could I avoid those faults? Could I put extra layers of test in? Would one tool detect the error in the previous one? And if you think that there may be a significant chance that a fault might leak into the system, you have to go into something called tool qualification. Final point I've got at the bottom is that every evaluation you do is unique to a specific tool version. So if you upgrade your compiler, you have to redo all of your qualification work, which is, again, quite a lot of what you see if you're a compiler or a tool vendor, and you say, well, why don't you just upgrade to the latest version? And you'll find that people are remarkably reluctant to do that. It's because they have to do all of the work that they've done previously all over again. So quite often you'll find that they would rather have a workaround or to know the various parameters of a fault rather than have a fix in a new version of the tool. Okay. So here's just a sort of graphical example of a tool flow and how a sort of safety-related developer might think about something. So here I've got a sort of example that could happen. It's pretty much fabricated, but you can imagine you have a model, and that model's generating C source code, and it's sort of and you can give that model test generator, and it will test data, and it can evaluate that test data itself. The idea is it's like model-driven development. You sort of develop all of your code in a sort of graphical package that can take test data and run. But when you actually want to put the code that the model's developed onto a device, you would generate C code, compile that C code. And you can see that this is a sort of simple flow, that you can see where various sort of bits could go wrong. and how you can do different checks. So for example, we feed the test data that we give to the model to the executable, and we can double check to see that they've given us the same value, which gives us a good idea that the system's doing what it ought to be doing. So some of the things that you can sort of say for a sort of functional safety advice is you can go along each bit and say, well, okay, what if that test generator gave me bad test data? What would be the consequence of that? What if the C source code was bad? Would the compiler or linker catch errors in that? And you can go through and say, what's the chance of that happening? That sort of thing. So these are the sort of things a safety-related developer would have to do for their sort of tool chain. Okay. So, yeah?
My point.
So the certification, is
Yes.
it a probabilistic process where you certify that you are compliant with to a certain probability, or is it 100% certainty?
So one of the principles of the safety is that they know that there can never be 100% in everything. So typically for hardware, there are random faults that could happen. So everything has to be done probabilistically. In software, it's assumed that the system is deterministic, but it's not assumed that you will provably have no bugs. And in fact, what the main way that the safety standards deal with this is that you must take steps to avoid all known issues, is what's written in the specification. So as a tool provider, it's up to you to document what the known issues are in the tool. And if the safety-related developer can say, I've taken steps to avoid the known issues, then I'm okay, if you see what I mean. A lot of it's also down to validation. So one of the things I'm going through here about, this is something called tool qualification. So this is an idea where you say, okay, I've looked at my previous tool flows, and I've judged that if there's an error in one of these tools, and I can't guarantee or have a very, very high probability that I'll be able to track it, that there'll be an error in the final system, I have to go through something called the tool qualification process. And this is where you have the various methods that they can do to look through that. Now, of these methods, only really 2 of them apply in practice. The first one, increased confidence from use. This is very much for, I had a tool from an earlier system where the functional safety standards didn't exist. I'm using that tool in exactly the same way as I've always done for the past 20 years, and it's always worked, and I've got all of this evidence that it works. Therefore, I think it's safe to use, just because of all of the years of experience that we've had. Now, if you're doing a new development tool, you can't make the excuse that, oh, it was developed before the safety standard. And for software, you have the actual conditions for increased confidence use are pretty much you're using the exact tool in exactly the same way, and that pretty much never happens. So the first case is ruled out for almost all of the cases. Tool is developed according to a functional safety standard. This is one where practically no modern development tool is developed according to a modern functional safety standard. It basically would be too expensive to, say, redevelop GCC or Clang completely from scratch using a safety-related standard. So that's mainly used for if you've got an internal tool and that you know that you can follow the same process you're using for the rest of your software, you can use that method. So typically what we end up falling back on is the second 2 ones here. One of the things that I'll be sort of going through here is what proportion of weight you put in each of these arguments often depends on where your tool is strongest. So for commercial tools, where you have a lot of the, you pretty much have a V model like development model, you've got a very stable set of developers, you know every change that's come in and you are in control of every change, then the most common way is to go through the evaluation of the development process, because pretty much you've got your development process written up internally anyway, and it's pretty much a matter of writing it up and mapping it to the V model. Now, for open source software, evaluation of the development process isn't going to go very well, because you've got hundreds of contributors, you've got no stable set of requirements, you've got lots of you haven't got an easy mapping to the V model. But what you can do is...
what they do have is a very rigorous code review.
Yes.
So
yeah, so the rigorous code review feeds into the validation of the software tool. And this is basically the, well, I don't quite know what went into making this tool, but here's my specification of what it does, and I can show by validation that it does that. So typically for an open source tool, you would figure way more weight into the validation of the software tool than you would do for the evaluation and development process. And I think the evaluation and development process is mostly used because it's probably easier to do than the validation model. I'll go into this into a little bit more detail later. Okay, so you'll often hear these words said as if they were the same thing, of qualification and certification. So you'll see quite a lot of products claim that they are certified for use, as suitable for use in some particular functional safety standard. Now, what does that certification actually mean? So certification isn't part of the actual standards themselves. These are third-party companies, trusted third-party companies. For example, there are many of these companies called TÜV. So there's a TÜV Nord, TÜV Rheinland, TÜV Süd, companies like Exeter, that type of thing. And what they're basically saying is, I can look at the development process of this tool vendor, and I can do some of the qualification work for you. I will say this is a known use case that this tool has. And as long as your use case of this tool is very similar to the use case that we've looked at, you can reuse the effort that we've done for qualification. So when something is certified, it doesn't mean that it's officially certified by the standards body. It means that there is a trusted third party that's looked at it. It's not compulsory, but it is quite often compulsory for a commercial vendor, because quite often, is there in any sort of commercial, say, development tool market, if a tool has certification and the other tools don't, most of the customers will buy the certified version because it simplifies the amount of qualification work that they have to do. So even though it's not required by the standards, it becomes required by the market pretty quickly, because a lot of the times it's a way of offloading some of this qualification costs.
Like a certificate of authority on the web, isn't it?
Yes, it is, yes. So quite often you'll see lots of these things being sort of promoted by tools. And I think that this is something that may be more used in the commercial market than the open source market. I don't know. It depends whether you see open source tools as directly competing with those tools, or it may be in areas where there is no competition. They may not be required. Okay. Final bit of clarification about compilers and development tools and software components before I go into sort of ARM compiler sort of experience. Is, you remember I mentioned before about you have this big mapping from requirements to implementation. Now, a compiler is thought of as a translator. It takes a customer's requirements, including all of their safety requirements, customer's implementation, customer's design, customer's source code. The compiler translates it into object code. But in theory, you've got a mapping all the way from the requirements to the object code, and you can show that either via tools or via looking at the actual disassembly itself. Now, the libraries, say for example the C library that you get with a compiler, it's not the customer's requirements, it's not the customer's design, it's the compiler writer's design, and so you can't treat those as the same thing, because the person who wrote all of the safety requirements didn't write the software or do the design of the actual software itself. So the actual libraries and compiler are a software component, and they have to go through a different part of the qualification process, and they quite often need a lot more effort to qualify. And this is the sort of thing that if you were going to, it's pretty much the same as if you were going to say, qualify a bit of open source software that isn't a development tool. It would have to go through this sort of component type process that's slightly different to developers. Now, I'm going to very briefly mention these, you might see it elsewhere, is there's something called a safety element out of context. This is what the hardware goes through. So if you see the CPUs, they'll say, we are a safety element out of context. And what that means is we've developed our component to a functional safety standard, but because it's a generic reusable component, we can't know how it's going to be used. So what the customer has to do, or safety-related developer, it has to map the context-less environment of the safety element out of context into their environment and say why it's safe. But in order to get a safety element out of context, you have to start the development from scratch with a sort of ISO 26262 approved sort of development process. So that's not an option for an existing software component. So typically the process that we go through is the qualification of software components, which is a separate part. Okay, so I've mentioned all of this, that it's the responsibility of the end user to do the sort of tool qualification. What can a tool chain provider do to make things interesting or help things along? So what I'm going to sort of go through is the qualification process that ARM Compiler 5 and ARM Compiler 6 went through. So the actual details of what's in ARM Compiler 5 and ARM Compiler 6 isn't particularly that important. The main context of distinction is that ARM Compiler 5 is entirely proprietary, but ARM Compiler 6 contains an open source software component as the compiler. So that's derived from Clang and LLVM. So we had to go through a slightly different process to get that part of the toolchain qualified. Okay. So what can the toolchain developer do to help? So it can't say for certain that the use of the tool will be safe in a particular environment, but it can provide an awful lot of useful information. So first thing, as I mentioned before, it can get certification for common use cases. It can write down which of the features of the tool are most useful. It can provide comprehensive documentation on how the tool should be used. It can provide functional specifications of the tool that the vendor can check. But quite often the most important bit is known faults and mitigations. So one of the things that we found most valuable about the information coming with the ARM compiler is what are the defects? And which versions of the tool do they affect, and how do I work around those defects? And that's probably the most useful and the most time-consuming and expensive to maintain over time. Right. So on Compiler 5, so whatever's in the software, one of our strengths here were that with the toolchain was that because it was proprietary, we had a good set of documentation. We had a single issue tracking system covering all of the changes in the compiler. We had a policy of citing an issue tracking number in every change that we made. So that kind of gave us an implicit traceability from the source code back up to our issue tracking system and hence our requirements. So anyone could do for a particular line of code, git blame, oh, there's my source code, there's my Jira commit number, I can look up in Jira to go and find the requirements for why that change was made. Because we controlled everything that went into that tool, we could enforce that policy. All of the committers to the project were ARM staff, we knew who they were, we could write on their training record with HR that they'd been trained in functional safety. So you can see it kind of heavily influences that we've got something here that we can write up as the V model. And that means that we can put a lot of weight on the evaluation of the tool development process to go through the sort of qualification. Okay. So just to sort of show what the actual final output with that was that we had a safety-related release. We released something called a qualification kit that went along with that release. So with that qualification kit, we had some documentation. I mentioned this mainly for the term the safety manual, what you see. So the safety manual is basically a required bit of documentation that any sort of tool or software component that's going to be used in a safety-related system has to have. And it's basically saying, how do I map this context, this element, into your safety-related sort of system? So for a development tool, it might say, here are the features that we are going to support for safety-related development. Here are the features that we're going to exclude from safety-related development. So we might find that from Compiler 5, we were heavily targeting the embedded market. And so we basically said at the time, our C++ library is from an external vendor. We know that most of the people in the safety-related area are not going to be using that C++ standard library. It's going to be a huge amount of effort to write up the bugs in that area, and we may not even have the capacity to fix them when they're there. So we made the decision, and we're going to exclude that part of the product from the safety release. It's up to you if you want to use it. The functionality is there, but if you want to go through the qualification process, there won't be any additional information for you in this document. You're on your own at that particular part. And one of the things that we were able to do, let's say, was go quite comprehensively, was take our JIRA issue system that had been tracking defects and also generate a defect report document which sort of has our all of the defects in the product that affect safety and how to detect the problem, how to work around it, that type of thing. Okay, so on to ARM compilers. Well, actually, it's just a little bit of a brief diversion here.
Eric Raymond.
Yeah. So one of the things that we were thinking about how do I explain what makes open source special versus a proprietary system, and it's not the actual part that the fact that a tool is open source or proprietary doesn't matter at all. The property that it's open source is not necessarily a good or a bad thing. What the functional safety standards people are looking for is traceability. They're looking for documentation. They're looking for known committers. They are looking for people who are trained. They're very much looking for a cathedral. And they're looking for things that they can map very easily to the cathedral V model that they have in their document. Open source, whilst it can be designed with a cathedral model in mind, and there are products that do that, the traditional, or at least the stereotypical model is that of the bazaar, where you have lots and lots of potential companies with a sort of meritocratic approach of all commits coming in. The good ones survive over time. You have good test suite. You have, they produce functionally the same sort of results in terms of quality, but you don't necessarily have that fixed set of people that you know, or you have got that fixed set of traceability from all of the particular inputs.
But you could potentially organise that.
Yes, there's nothing. Yeah, that's why I mean I say rather than say open source versus proprietary, it's really the cathedral versus bazaar. And the approach that we used for the open source component tool, and I think it's the one that's most heavily used when people do want to take open source components into here, is you basically build a cathedral on top of the bazaar.
Well, which fits, in medieval England, they would hold the markets in the cathedral.
Right, okay.
It was out the weather, right?
Yeah, so I think one of the things that, so this is just basically following on from that ARM compiler 6. The main differentiator between ARM compiler 5 and ARM compiler 6 is that the compiler is now based on Clang. So what we do in our sort of development process, we take regular we basically merge with upstream incredibly frequently. So what that means is that the proportion of commits from upstream vastly outweigh the proportion of commits from downstream. So it's really not our tool at all. It's upstreams plus a little bit of ARM configuration to make it work well with the rest of the tools. So upstream Clang follows a very loose development process, mailing list driven, many committers. You have the same review and quality process that's going on, but the tool itself, not particularly well documented. Its documentation is very much, well, we kind of do what GCC does. Go see the GCC documentation. and even then, the GCC documentation is not great either in a lot of areas. So how are we going to go and get this particular tool qualified? So what we decided to do in this particular case was we'll say, okay, we'll never be able to win with a development process argument, but what we can do is say, well, okay, let's focus on validation of the software tool. So we invested more in third-party test suites. You can do your own internal test suite, but if it's a known industry-supported test suite that anyone can buy and configure, they can at least try and reproduce your results. So we basically went through on the idea of we've taken this upstream tool that we don't necessarily know where it's come from, but we're going to snapshot it. We're going to say, from this point onwards, we're not taking any more changes from upstream. This is the point where you slap the cathedral on top of the bazaar, and then you then say, we are only going to allow changes on this particular branch that we've gone through a very rigorous change process on. And what we're going to do is we're going to document, with our own tech comms people, what our supported feature set is.
And that's typically very, very expensive.
It is,
and
yes.
therefore done very rarely.
Yes. So this is why you'll often find that there are very few examples of open source tools that have been qualified, mostly from the sort of requirement that you have to provide a functional specification and then the validation tests. And quite often you don't have that functional specification. Somebody has to go and reverse engineer it, basically. And for certain tools, that's easier than others. Now, perversely, for as complicated as a C and C++ compiler is, it has the huge advantage that of the C and C++ standards have already been written. So pretty much the documentation for those tools is what are the options that you support that configure how you interact with these already existing documents known as the C and C++ standards. There are third-party standards conformance test suites that you can run. So your job as a compiler author is actually a lot easier than if you were sort of a tool that didn't sort of operate in a very standards-driven environment. So, yeah. But basically what I'm basically saying here is that the strategy for an open source tool to take that, and even a component, is you have to pretty much snapshot it, reverse engineer the documentation that you need, and then only take it forward with very carefully controlled updates, which you could say, well, okay, I'm kind of losing almost all the benefits of the community when I do that. So how you find a model for this that works over time, difficult. So what we're kind of doing at the moment is saying, keep the release cycle very long for our safety-related release. We're not going. We don't want to keep updating it frequently because it's going to be very expensive each time. But what we can do is to say, every few years we take a branch off upstream trunk, update our documentation to match, then provide a very small drip feed of updates from that particular time. I think you find that the safety-related industry is very much more conservative about its usage of tools and its need for the latest features. So you can quite often have a much slower update cycle for this particular thing.
But then you end up paying the cost every time you update, the full cost.
Not necessarily the full cost. If you've got, for example, if you think, how much has Clang changed from, say, Clang 3.0 to 5.0 in terms of actual usability, visible changes? Internally, it's a huge change, but externally, how much would you change?
But that's the thing. I mean, if the core of it changes a lot, then you can't have the same guarantees. You can't assume almost anything from the past. Like if the whole code generation changes, like globalized cell, for instance.
Yeah, but that's why you have validation tests. So
no,
validation
which
tests
means you have to pay the whole cost again.
Yes,
validate everything from scratch.
Renato, inevitably, and this is a theme I'll touch upon in my session as well, you kind of don't have most of the software changing, that's the assumption you run with, right? So some of the microkernels that are used in the safety space, for example, the code of the microkernel rarely changes because it's boiled down to the barest minimum bits you need. Right? Now, so there is an assumption here that your software is actually not changing drastically. There are bits of it that you can keep out of scope for the next edition of the kind of certification, qualification bits, right? But if it's changed completely, then yes, you pay the cost. But I think you mitigate that by doing this less frequently, because the industry doesn't really want the bleeding edge features.
Exactly. Yeah. If you have a tool from 15 years that still work.
One thing I'm not going to be able to say is that this is not going to be cheap. It is expensive, whether it's an open source tool, whether it's a proprietary tool. A lot of the costs are going to be much the same, unfortunately.
Another thing worth keeping in mind is that when you start treating safety as an objective, you have to be comfortable with two things. One is this is going to cost you money, but you probably will end up saving lives. Probably, not guaranteed. And well, basically, that's the killer one. It's just the fact that you're going to have to pay. The second one is even less palatable to a lot of people who are new to safety, which is you're going to compromise on performance.
Yeah.
Because the moment you start optimizing for safety, you put in safeguards into your architecture, which mean you're going to lose performance.
Yeah.
Right? So stop doing performance benchmarks.
Okay. Okay, so just some of the lessons that we learned from this. is that snapshotting the development tool, validating it and controlling the updates is a viable approach. What we did to start with this was to, and I think I'll go to the bottom point here first. We got a proof of concept ready from our certification authority first before we did this. We didn't spend an awful lot of money, and then went and phoned up the certification authorities and said, "Hey, can we do? What do you think about this?" We carefully went and spoke to them beforehand and said, "We're kind of thinking about doing this. What do you guys think? What bits do we need to focus on? What bits are no-go areas for you?" And so we spent quite a bit of time up front saying, basically talking to the certification authorities and trying validating the approach before we did it. So that's definitely one of the things that's worth doing. Getting the supported feature set right is probably your most important decision, because if you say, it's kind of a double-edged sword, the more that you cut out of your product, the less you have to write and the less your customers have to read and understand. But what if you cut out a feature that one of your safety-related customers absolutely must have? So really it's a case of how do you find a feature set that is useful for the most customers, but you can kind of cut most of the things you don't do. The largest chunk of your actual long-term costs, actually once you produce the documentation to start with, that will remain fairly stable because you're not changing the product very much. The bit that you do have to pay a lot for is writing up the defects. For example, many of you will be, when you find a bug in GCC, it won't just be that the bug that some guy introduced last week. The chances are that bug might have been there for 2 or 3 years, and it might, well, if you find a bug that is actually on your old piece of software, you still have to write it up and communicate it to the safety-related developers. So one of the biggest long-term costs on your development team is working out how are you going to communicate the long trail of bugs to your customers. I guess the standard thing of automate as much of the information tracking as you can. Our defect report is driven directly from Jira by basically Python scripts that pull the information out and then format it. If we actually had to have a tech author go through and pull all that information every time, that would again add to the costs quite significantly. Runtime libraries again, lead to the point.
How competent are certification authorities in open source development and in toolchain development?
The toolchain, I can't answer for open source development. I can answer the toolchain. They obviously knew what a compiler was at a high level, but their general approach were, you guys are the experts. We trust that you're producing a quality product. What we know is development process. What we need to know is how does your development process map to our development our model of the world, so that we can see the evidence to sort of back up the idea that you know your stuff. So they will not go through and quibble your defect reports. What they'll say is the process that you use to produce those defect reports. They'll look at how many reviewers you have. Does somebody look at it to make sure that a safety-related developer would look at it? So they wouldn't look at the actual technical content, but they would look at the development process that they do understand to sort of try to work out, is this development process going to produce a good result if everybody is competent, is their approach.
So I would imagine that certification authorities would be comfortable with cathedral mode of development, but
yes.
not with Bazaar.
Yes.
So the cathedral was their idea to slap on top of a Bazaar or ARMS?
Well, it was our idea, or well, I say our idea. It was an idea that we had seen had worked in the past. So ARM is not the first company to get an open source tool through the certification authority. So we looked at what other companies had done, and we sort of chose an approach that we thought was most likely to work based on what the strengths of the tool were. There is some, as far as I understand, open source development methodologies, or the only public quote that I managed to find was that a pure open source Bazaar model isn't recognized by ISO 262, but there have been some limited bits or limited circumstances where certification authorities have approved open source models, and I think it's mainly just it's something that's getting more traction. One of the things also that the industry controls the standards. So if the industry wants to use open source software, it will find a way. These software, so I think that one of the things that Linaro could do, ARM could do, if open source needs to be in the next versions of the standards, they need to be lobbying the standards people to say, okay, how do we put measures into these to make sure open source is part of a recognised model? They won't compromise on safety, but if you can provide arguments as to how to do it right, then I think that's probably the best way forward. Okay. So just my very last concluding thoughts, I've got to wrap this up. For Linaro, on the assumption that you may want to take some of the tools that you're providing and qualify them. Snapshotting is a way that we know has been done, at least as an existence proof that works. Providing the information is very expensive. Upfront documentation, there's an ongoing service to tracking the bugs. It's going to be expensive, whatever you do, and you're going to have to probably track contributions a lot more carefully and probably act very much more as a cathedral-like organisation rather than working directly upstream. Now, I don't know quite how that will work in the context of Linaro. I guess that's not my job to work out. I guess that's for the people at Linaro to sort of work out how that sort of things will go. But I think things are changing to move towards the open source direction, because I think, as you mentioned, open source is becoming much more prevalent, and I think it will get much more, the industry will get much more familiar with it over time. But yeah, so I better conclude there. I don't know how much time we've got for questions, probably not very much, but 2 minutes. So yeah, so okay, yeah. I will be around in the toolchain group and around in general, so please just do chat.
Just a quick question. You mentioned you only looked at C. Do you also support certified C++ compiler?
We do in the kind of, so what we did is we split out the libraries from the language. So we said the C++ core language, so the runtime library is basically new and delete, but not the standard library, with exceptions and all that sort of thing. But yes, we do support the standard C++ language. How much of use that actually is to people, I don't know.
Version 5 or 6?
In both of them, so yeah.
Good question. So, so your strategy relies on snapshotting.
Yeah.
My question is, how often are you going to be snapshotting, and how long will you support those snapshots?
So typically we was, I can't remember precisely how long ago. I think between snapshots we're probably talking a minimum of 2 years, and I think the support is often long term. Probably coming up to 5 years. Mostly because the tool when people buy these things, they want them for a product that's going to live a long time. So typically the commercial requirements will force you into a very long period of support. So yeah, we expect to be maintaining these long branches for quite some time.
Okay, and I presume too that for a 5-year link, there's going to be manning parallel as well that you support.
What's that, sorry?
There will be multiple releases you support in parallel. Since
Yes. Yeah, so it gets expensive, unfortunately, for that particular part. So ideally, we have to choose the point to snapshot where there's probably going to be a point where ARM IP changes significantly between the releases, so that we need a new version of the compiler to support new ARM IP in the market. So that's probably where the release for us is, we choose to release when there's new ARM IP we have to support, that type of thing. Okay. I say, I'll be around, and if anyone wants to come catch up with me anytime, then don't hesitate. Okay, I better stop there.